Inside a turbine engine, bearings, gears, and accessory drives operate at extremely high speeds and temperatures. Without a constant supply of oil, these components could overheat and fail within minutes. That is why every turbine engine relies on a carefully designed lubrication system to cool, protect, and lubricate its moving parts. In this video, we will explain how a turbine engine lubrication system works, including the pressure, scavenge, and breather subsystems. We will also compare dry-sump and wet-sump systems and show how oil flows through the engine from start to finish. By the end of this video, you will have a clear understanding of how turbine engine lubrication systems keep modern aircraft engines operating safely and efficiently. A turbine engine lubrication system has several important jobs. It must lubricate bearings and gears, reduce friction and wear, remove heat from engine components, carry away contaminants, help seal bearing compartments, and protect moving parts from damage. Most turbine engines use a dry-sump lubrication system because it can carry more oil and control oil temperature more effectively. A typical dry-sump pressure-regulated turbine lubrication system has three main subsystems: the pressure system, the scavenge system, the breather system. The oil is stored in a separate oil tank mounted on the engine, usually near the compressor case. The pressure system sends oil to the engine bearings and accessory drives. The scavenge system returns the used oil back to the tank. And the breather system removes trapped air and maintains proper pressure throughout the engine. Let's begin with the pressure system. Oil leaves the oil tank and enters a gear-type pressure pump located in the accessory drive housing. The pressure pump raises the oil pressure and sends the oil to the oil filter. The oil filter removes contamination before the oil reaches sensitive engine parts. If the filter becomes clogged, a bypass valve automatically opens so the engine still receives oil. From the filter, the oil flows to a pressure-regulating valve. This valve keeps the oil pressure at the correct level regardless of engine operating conditions. The regulated oil then passes through a fuel oil cooler. The cooler removes excess heat from the oil while at the same time warming the fuel. After cooling, the oil travels through last-chance filters and finally reaches spray nozzles. These spray nozzles direct a steady stream of oil onto the engine bearings. Because the nozzles use fixed orifices, the bearings receive nearly constant lubrication at all engine speeds. Once the oil has lubricated and cooled the bearings, it must be returned to the oil tank. This is the job of the scavenge system. Unlike the pressure system, the scavenge system usually uses several gear-type pumps. In this example, there are 5 scavenge pumps. Each pump removes oil from a different bearing compartment or gearbox area. The number 1 bearing scavenge pump removes oil from the front bearing case. Oil from the number 2 and number 3 bearings flows through internal passages. Oil from the number 4, number 4 1/2, and number 5 bearings is collected in another bearing cavity. The rear turbine bearing scavenge pump removes oil from the number 6 bearing compartment, sends it through a passage in the turbine case strut, and then directs it to the number 4, 4 1/2, and 5 bearing cavity area before all of the oil returns to the oil tank. All of this oil eventually returns to the accessory gearbox and then flows back to the oil tank. But there is one problem. The returning oil is mixed with air. To solve this, the oil enters a deaerator inside the oil tank. The deaerator separates the air from the oil. The oil stays in the tank, ready to be used again, while the air continues into the breather system. The breather pressurizing system performs 2 important functions. First, it maintains the correct pressure inside the bearing compartments. Second, it helps create the proper oil spray pattern from the bearing nozzles. Breather tubes connect the bearing compartments, the oil tank, the compressor section, and the turbine section. These tubes carry air and oil vapor to a component called the deoiler. Inside the deoiler, the oil is separated from the air oil mist. The recovered oil returns to the lubrication system. The remaining air is vented overboard. This keeps the lubrication system balanced and prevents excess pressure from building up inside the engine. Many large turbofan engines use a variable pressure dry-sump lubrication system. This system still uses the same 3 basic subsystems: pressure, scavenge, breather. But there is one major difference. There is no pressure regulating bypass valve. Instead, the oil pressure changes with engine speed. As engine RPM increases, the oil pump spins faster and the oil pressure rises. For example, oil pressure may vary from about 100 psi at low speed to more than 260 psi at high power settings. A relief valve is still installed, but it only opens if pressure becomes dangerously high, usually around 540 psi. In the variable pressure system, oil leaves the tank and enters the pressure stage of the oil pump. A slight pressure inside the oil tank ensures a steady supply of oil to the pump. After the oil is pressurized, it flows through the main oil filter. If the filter becomes clogged, the bypass valve routes the oil around the filter. Next, the oil passes through an air oil cooler. When the oil is cold, it bypasses the cooler. When the oil is hot, it flows through the cooler. The oil then continues through a fuel oil cooler. Some oil also flows through a trim orifice that helps maintain oil pressure at low engine speeds. Finally, the oil passes through last chance filters and reaches the bearings, gearboxes, seals, and accessory drive splines. The scavenge system in a variable pressure lubrication system is similar to the regulated system. Several scavenge pump stages remove oil from the bearing compartments and gearboxes. Each scavenge stage includes a magnetic chip detector. These detectors trap metal particles and provide an early warning of bearing or gear damage. After the oil reaches the tank, the deaerator separates the air from the oil. The air is then vented overboard through a check valve. The breather system also uses a deoiler. The deoiler spins at high speed and separates the oil from the breather air before the air is vented overboard. Although most turbine engines use Dry-Sump systems, a few engines use a Wet-Sump lubrication system. The main difference is the location of the oil reservoir. In a Dry-Sump system, the oil is stored in a separate tank. In a Wet-Sump system, the oil is stored directly inside the engine, usually in the accessory gearbox or in a sump at the bottom of the accessory case. A typical Wet-Sump system includes a sight gauge to check oil level, a breather or vent, a magnetic drain plug, temperature, and oil pressure fittings. In a Wet-Sump system, some bearings and gears are lubricated by splash lubrication. As gears rotate through the oil, they throw oil onto nearby components. Other engine parts still receive pressurized oil from a pump. The oil passes through a filter and then through jet nozzles that spray oil onto bearings and couplings. After lubricating the engine, the oil simply drains back into the sump by gravity. This makes the Wet-Sump system simpler than a Dry-Sump system, but it usually carries less oil and offers less control of oil temperature. Let's quickly review. A turbine engine lubrication system stores oil in either a Dry-Sump tank or Wet-Sump reservoir, uses a pressure system to deliver oil, uses a scavenge system to return oil, uses a breather system to remove trapped air, and keeps bearings, gears, and accessory drives cool and protected. Dry-Sump systems are used on most turbine engines because they provide better cooling, better oil control, and a larger oil supply. Wet-Sump systems are simpler, but are less common. Thanks for watching.